In my recent DFMA video, one of the design for manufacturing and assembly improvement was to provide an undercut relief at the shaft shoulder. Simply because in machining, turning tools are never perfectly sharp. So during turning operation, the tool always leaves a small inherent fillet at the shaft shoulder. Now, by itself, this radius is not a real problem. But if the shaft is designed to fit inside a mating part hole, then this small inherent fillet can prevent the mating part from sitting properly flat against the shaft shoulder face. And this problem can be simply solved by providing an undercut relief at the shaft shoulder. So the mating part can always rest properly against the shoulder face without any interference. But after that video, the comment section suddenly started flooding with your comments that this design is awful, it's weakened the shaft, it's increasing the cost, you are exaggerating the fillet size. And almost all the comments comes down to one common argument. Why not simply leave the shaft shoulder as it is with the tiny inherent or whatever fillet and instead add a small chamfer on the mating part hole, something like this. That way the part will still fit together properly, sit flat, cost less, and the shaft will remain much stronger as compared to using an undercut relief. Too logical, isn't it? Does this mean I'm designing the shaft with undercut relief for a decade? It just doesn't make any sense. Is this just an old manufacturing practice that designers like me keep repeating blindly? And we ignoring the modern easiest solution? Just chamfer the hole. Well, let's figure it out. Now, the first thing first. Many of you assume that undercut relief is only required for soldered bolts, just because I used solder bolt in that example. But the undercut relief is applicable for many other precise stepped shaft. Whether it's a ball screw, a gear shaft, or any custom design shaft where the shaft shoulder need to sit flat against the mating part. Second, yes, in that video and on thumbnail, I scaled the manufacturing inherent fillet size, not to prove my point, but simply to make that tiny corner fillet clearly visible. So let's first understand how much corner radius actually forms during the machining operation. So in most of turning operations, the size of inherent corner radius is mainly determined by tool nose radius, TNR of the cutting insert. So why not simply use a perfectly sharp pointed tool? Because a very sharp pointed tool would break very quickly under cutting force. Also, the surface finish is mathematically related to feed rate and nose radius. If the tool radius becomes too small, the surface finish becomes rough and unstable. This is why any turning tool or insert are manufactured with a specific nose radius, typically range from around 0.2 mm to 1 mm. And as the tool wears, the effective nose radius also increases. So in real manufacturing, even if no corner radius is defined in drawing, the final machined shaft step will always have a small tiny corner radius at the shoulder, exactly equal to effective nose radius of the turning tool. And that small radius interferes with the mating part and prevent the proper full face contact. As a result, the load do not distribute properly across the shoulder face, which leads to localized stress concentration, vibration, and wearing or damage over the time. And in precision assemblies, this also creates dimensional and alignment issues. So to solve this problem, if you think from geometrical point of view, the simplest and economical solution is to just provide chamfer at the mating part hole, something like this. So the shaft staff with that corner fillet can fit inside the chamfer, and the shaft shoulder can sit flat properly against the mating surface. And yes, I agreed. There is nothing wrong with this approach as per a geometrical and economical point of view. And to implement it, you just need to define the allowable corner radius in SAP manufacturing drawing and also define the chamfer size in matting part drawing. A better practice is to define the shaft corner radius as a maximum radius. 0.5 millimeter is optimum for a shaft corner. So the manufacturer can maintain anything equal or smaller than 0.5 millimeter. And you can define a chamfer size 1:45 to clearly avoid interference with 0.5 millimeter radius. So if this solution is already as simple and economical, then why do we even need undercut relief at all? Why do ISO standard for undercut relief exist? And why do we still see undercut relief used in many standard machine components? So the first reason is precision machining. When a shaft required a precision fit such as H7G6, the final dimension not achieved directly by the turning. During turning, the machinist intentionally leave a small amount of extra material called grinding allowance. Then the shaft goes under cylindrical grinding for final precision sizing and surface finish. Now, in cylindrical grinding, the grinding wheel do not have a fixed tiny nose radius like a turning insert. The effective edge radius of grinding wheel continuously changes depending on diamond dressing condition, dressing frequency, and wheel wear. Also, the grinding wheel cannot properly reach a sharp step corner because if the wheel is pushed fully into the corner, the side face of the wheel may start touching the shaft shoulder face itself. At the same time, coolant flow near the corner becomes restricted. As a result, shoulder perpendicularity can be disturbed. Thermal burning mask may appear. And if wheel not reach the corner, it leaves an unground step or excess material near the shoulder. But imagine if an undercut relief is provided, the grinding wheel can freely pass through the entire shaft diameter without interfering with the shoulder face. This allows complete grinding up to the functional edge, proper coolant access, and more consistent grinding finishing. And this is exactly why undercut relief is also commonly known as grinding relief. So whenever a shaft is subjected to cylindrical grinding, precision fit, or high accuracy shoulder sitting, undercut is not an option, it becomes necessary. But if it is only a general purpose shaft, no precision fit is there, then the chamfer method is usually completely sufficient. So is grinding only the reason why undercut is used? No. The most important reason behind undercut relief is interchangeability. Let's say you are designing a ball screw assembly, where at one side a float bearing arrangement is installed, and at the other side a fixed bearing block is mounted. Now, the fixed bearing block consists of a pair of angular contact bearings in back-to-back arrangement, including 2 spacer and 1 lock nut. And most of those spacer doesn't have sufficient chamfer. Another example, if you are designing a step shaft for mounting of gears, standard gears may or may not include chamfer at all. So if the ball screw step or the gear shaft step doesn't have undercut relief, the proper sitting can never be fully guaranteed. Also, in real machine design, one designer may design the shaft, while other designer designing the matting component. So if you are not providing an undercut relief, then you will be always have to depend on other designer to remember to add chamfer in their matting part. Also to define the correct chamfer size to maintain compatibility with your shaft corner radius. And that leads to assumptions and guesswork. So it's better if shaft itself guarantees its own fitment. It ensures the reliable assembly and true interchangeability between the parts. And this is one of the biggest reasons that why undercut relief become standardized in ISO system. Because standardization is not only about the geometry, it's about ensuring the independently manufactured parts will always assemble and function together properly. Now, the third reason that most of engineers misunderstood. Most engineers assume undercut relief weaken the shaft. And yes, if you are only talking about pure physical strength, then technically the undercut does reduce the shaft diameter and therefore shaft strength also decrease slightly. But in practical machine design, this usually shouldn't become a major problem. Because while designing a shaft, you never select a shaft diameter exactly equal to minimum required strength. A proper shaft design always includes a reasonable factor of safety, typically around 2 to 3 times depending on application. So if the undercut only removes around 1 or 2 mm locally, then depending on the original shaft size, that a small reduction usually do not create a serious strength issue. The real problem is stress concentration and fatigue failure. A sharp corner at shaft step create very high stress concentration, have very high stress concentration factor. And that tiny inherent fillet is usually too small to significantly reduce the stress concentration. So instead, it's better to use undercut relief like type F or type H, which are designed with larger transition radius, especially for high fatigue loading application. These profiles actually improve the fatigue resistance because they allow a smoother flow of a stress line compared to sharp shoulder corner. Whereas for normal duty or low load application, standard relief type E, type G are usually sufficient. You can find the detailed dimension in a standard like ISO 18388 or DIN 509. Or in many general application, you can simply use basic undercut relief similar to this design. Now, there is also an underrated reason, and that is inspection difficulty. If there is a small, not fully controlled corner radius, then how will inspection engineer accurately verify the shaft diameter up to a specific shoulder length? How they will know exactly up to which point of the diameter must remain within the tolerance? Because near the corner radius, the diameter gradually blind in shoulder. So the effective inspection boundary becomes unclear. So if the undercut relief is provided, the gauge can fully pass and sit properly up to defined shoulder location. This creates a clear inspection boundary and makes the dimensional verification much reliable and repeatable. So if you think from pure geometrical point of view, the chamfer method may seem more logical and economical. But from the perspective of manufacturing ease, precision grinding, interchangeability, inspection reliability, and stress concentration reduction, undercut relief become better engineering solution. And my friend, this is exactly why mechanical design is complex. Because engineering decisions are rarely depends on one single parameter. A design that looks geometrically correct may fail in manufacturing, assembly, inspection, fatigue, standardization point of view. And this is why mechanical design is not just drawing the shapes. It is balancing manufacturing, function, reliability, cost, assembly, and long-term performance all together. So this is it for this video. I hope you found this video useful, this in-depth analysis video useful. And if you did, please give us a like, hype. Also not forget to subscribe. And thank you so much for watching this video.